Dear students, welcome back to another video lecture on the course Signals and Systems with course code 18EC45. In the previous video lecture, we discussed how a linear time invariant system can be analyzed in the Z domain. How do we obtain the output y of n of an LTI system with the help of the Z transform? In today's lecture, we'll be solving some more problems to understand transform analysis of linear time invariant system. And with these problems, we'll conclude module 5. The first problem we'll be considering is step response of an linear time invariant system is found to be y of n equals to 2 1 by 3 to the power n u of n. Find out the impulse response of the system. So difference equation which represents the linear time invariant system is given as y of n equals to 2 times 1 divided by 3 to the power n u of n. Taking Z transform, we'll get y of z equals to 2 divided by 1 minus 1 by 3 z inverse. Input x of n will be equals to unit step sequence u of n. Therefore, its Z transform x of z will be given by 1 divided by 1 minus z inverse. So writing this in the ratio form, which will give us the transfer function, h of z will be equals to y of z divided by x of z. So 2 divided by 1 minus 1 by 3 z inverse whole divided by 1 divided by 1 minus z inverse. Simplifying this, we'll get 2 times 1 minus z inverse divided by 1 minus 1 by 3 z inverse. Now rearranging the terms, h of z can be directly written in terms of standard Z transform notations. So h of z will be 2 times 1 divided by 1 minus 1 divided by 3 z inverse minus z inverse divided by 1 minus 1/3 z inverse. Now taking inverse Z transform, h of n, the impulse response, can be written as 2 times 1 divided by 3 to the power n u of n minus 1 divided by 3 to the power n minus 1 u of n minus 1. Now the second term here is different because it is multiplied by the z inverse. In the numerator we have z inverse, which is an delay element. So 1 divided by 3 to the power n u of n minus 1 will be delayed by 1 unit, and that delay will be represented in the power as by representing n minus 1 and u of n minus 1. So this is the impulse response for the system described by the given difference equation. The second problem we'll be taking is determine the impulse response h of n for the system described by y of n minus 0.6 y of n minus 1 minus 0.16 y of n minus 2 equals to 5x of n. We'll take the difference equation and apply Z transform on this difference equation, which will give us y of z minus 0.6 z inverse y of z minus 0.16 z to the power minus 2 y of z equals to 5x of z. Rearranging the terms to obtain h of z, the transfer function, h of z will be the ratio of the Z transform of the output to the Z transform of the input, y of z divided by x of z, which will give us 5 divided by 1 minus 0.6 z inverse minus 0.16 z to the power minus 2. So h of z for positive powers of z can be written as 5z square divided by z square minus 0.6 z minus 0.16. Or if we factorize the denominator, we can rewrite it as 5z square divided by z minus 0.8 and z plus 0.2. There are two poles, one at 0.8 and another at minus 0.2. Now taking the z inverse Z transform by partial fraction expansion method, we can rewrite it as h of z divided by z equals to, there will be two residuals applied for each of the pole, a divided by z minus 0.8 plus b divided by z plus 0.2. A will be calculated as z minus 0.8 multiplied by h of z divided by z when z will be equals to 0.8. By simplifying this, we'll get A's value as 4 and B will be calculated as z plus 0.2 multiplied by h of z divided by z for z value minus 0.2. By simplifying this, we'll get B value as 1. Using this, h of z divided by z can be written as 4 divided by z minus 0.8 plus 1 divided by z plus 0.2. Writing this equation, sending z to the other side and writing this equation for the negative powers of z, h of z can be written as 4 divided by 1 minus 0.8 z inverse plus 1 divided by 1 plus 0.2 z inverse. So writing the time domain equivalent terms, h of n will be equals to 4 times 0.8 to the power n u of n plus minus 0.2 to the power n u of n. Taking u of n common, impulse response h of n will be equals to 4 times 0.8 to the power n plus minus 0.2 to the power n u of n. In the next problem, we'll consider a causal and stable discrete time system defined by y of n equals to 5 divided by 6 y of n minus 1 minus 1 divided by 6 y of n minus 2 plus x of n minus 2 x of n minus 1. We'll have to determine the system function h of z and magnitude response at 0 frequency. Then we'll have to obtain the impulse response of the system and then the output y of n for the input x of n equals to delta n minus 1 by 3 delta n minus 1. We'll write the difference equation and take its z transform, which will give us y of z equals to 0.83 z inverse y of z minus 0.16 z to the power minus 2 y of z plus x of z minus 2 z inverse x of z. Combining the input and output terms and taking the ratio, h of z equals to y of z divided by x of z can be written as 1 minus 2 z inverse divided by 1 minus 0.83 z inverse plus 0.16 z inverse square. Writing for the positive powers of z, numerator will be z square minus 2z divided by denominator will be z square minus 0.83 z plus 0.16. Now Fourier transform can be obtained by z transform by using z equals to e to the power j omega. So in place of z, in the above transfer function, we'll substitute e to the power j omega. After substituting z as e to the power j omega, Fourier transform can be written as h e to the power j omega, or its equivalent notation is h of omega. So e to the power 2 times j omega minus 2 e to the power j omega divided by e to the power 2 j omega minus 0.83 e to the power j omega plus 0.16. If we substitute omega equals to 0 in each of the exponentials, all the exponential value will be equals to 1. Therefore, simplifying this, we'll get h of omega equals to minus 3 at omega equals to 0, or h of 0 will be equals to minus 3. Now to obtain impulse response, we'll consider the system function described by h of z equals to z square minus 2z divided by z square minus 0.83z plus 0.16 and rearrange this to apply the partial fraction expansion method. H of z divided by z equals to z minus 2 divided by z minus 0.33 and z minus 0.5. There are two poles obtained by the characteristic equation. We'll be having two residuals, a and b. If we calculate a as z minus 0.33 multiplied by h of z divided by z for z equals to 0.33, we'll get 9.8, which we approximate it to 10. A will be equals to 10 and b will be getting as minus 8.8, which will be approximating it as minus 9. So a value is 10 and b value is minus 9. Using this, h of z divided by z can be written as 10 divided by z minus 0.33 plus minus 9 divided by z minus 0.5. And writing this for the negative power of z by sending z to the other side, will obtain 10 divided by 1 minus 0.33 z inverse minus 9 divided by 1 minus 0.5 z inverse. Therefore, h of n, taking inverse z transform of each term, h of n can be written as 10 times 0.33 to the power n minus 9 times 0.5 to the power n u of n. Now to obtain the output y of n, for the input x of n equals to delta n minus 0.33 delta n minus 1, first we'll take the z transform of the input, which will give us x of z equals to 1, because 1 is the z transform of unit impulse function delta n, minus 0.33 z to the power minus n, because we have delta n minus 1 delayed unit impulse function, and its z transform will be z to the power minus n, and 0.33 is the coefficient or the constant associated with it. Now taking the ratio y of z divided by x of z will give us z square minus 2z divided by z square minus 0.83 z plus 0.16. Sending x of z to the other side, z square minus 2z divided by z square minus 0.83 z plus 0.16 will be multiplied by the value of x of z, which is 1 minus 0.33 z inverse. If we factorize the denominator, we'll get the roots as 0.33 and 0.5. So 1 minus 0.33 z inverse in the numerator and denominator will cancel. So we'll remain with 1 minus 2z inverse divided by 1 minus 0.5 z inverse. So rearranging it directly in the, or dividing the denominator between the two terms of the numerator, y of z can be written as 1 divided by 1 minus 0.5 z inverse minus 2 times 1 to 2 divided by 1 minus 0.5 to the z inverse multiplied by z inverse. So the second term have an z inverse. Y of n will be equals to 0.5 to the power n u of n minus 2 times 0.5 to the power n minus 1 u of n minus 1. N minus 1 in the power and u of n minus 1 is because we have z inverse term. And we'll understand, to write 0.5 to the power n u of n, we'll get to know the region of convergence, whether it will be a right-sided sequence or left-sided sequence, by the nature of the system. And this, in this problem, the system was defined as causal and stable. For a causal system, impulse response will be 0 for n less than 0. So it has to be a right-sided sequence. So we'll write the output y of n as 0.5 to the power n u of n minus 2 0.5 to the power n minus 1 u of n minus 1. In the last problem, we'll determine the z transform of two of the sequences by using z transform properties. And the first sequence we'll be taking is reflection of the unit step sequence, defined as x of n equals to u of minus n. And we know that z transform of the unit step function u of n can be written as 1 divided by 1 minus z inverse. For the region of convergence, mod of z greater than 1, because u of n is a right-sided sequence. By applying time reversal property, we studied while studying the properties of the z transform, or time reversal property states that x of minus n's z transform will be x of z inverse, or x of 1 divided by z. So for u of minus n, the z transform will be same, 1 divided by 1 minus z inverse itself. But the region of convergence will change. This time, mod of z inverse will be greater than 1, or sending z to the other side will get mod of z less than 1. For u of minus n will be a left-sided sequence. And for left-sided sequence, region of convergence will be within the circle. So mod of z will be less than 1. So this is the z transform and region of convergence for the reflection of the unit step sequence u of minus n. For the second sequence, we'll consider x of n equals to n times alpha to the power n u of minus n. Now for the exponential sequence, or for the exponential sequence which is present on the right hand side, we know the z transform, and its z transform is given by 1 divided by 1 minus alpha multiplied by z to the power minus 1. This is the z transform for the sequence alpha to the power n u of n, and the region of convergence will be mod of z greater than mod of alpha. Now if the power is negative, alpha to the power minus n u of n's z transform will be z divided by z minus 1 divided by alpha. This time the region of convergence will be mod of z greater than 1 divided by mod of alpha. By applying time reversal property, x of minus n's z transform x of z inverse alpha to the power n u of minus n's z transform can be written as z inverse divided by z inverse minus alpha inverse, where the region of convergence will be mod of z inverse greater than 1 divided by mod of alpha, or we can rewrite this z transform as 1 divided by 1 minus alpha inverse z, and the region of convergence will be written as mod of z less than mod of alpha. Now by applying differentiation property, we'll be obtaining the discrete time sequence for which we are finding the z transform, that is n alpha to the power n u of minus n. And by the differentiation property, we know that its z transform have to be minus z first derivative of 1 divided by 1 minus alpha inverse z. Now taking the first derivative and multiplying it by minus z, we can rewrite it as minus alpha inverse z divided by 1 minus alpha inverse z whole square. Rearranging this, we can rewrite it as minus of z divided by alpha, which will be in the numerator, divided by 1 minus z divided by alpha whole square, which will be in the denominator, and the region of convergence will be mod of z less than mod of alpha. So these are some of the problems. If you have any doubts, you can contact me. Thank you all and all the best.